Hello, good morning. So today we're going to be looking at factoring second degree expressions. So a quick note on what that means. Again, second degree. What this means is that you have something to the second power, right? So that the degree, the highest power in the expression is 2. Okay, if something was third degree, it'd be 3, etc. So these are things that have an exponent of 2. And again, to remind you, in the real world, these are things that are curved in nature, so not linear functions. They have a bend to them, so like falling objects are modeled by degree 2 expressions and functions. But we're not really dealing with these as functions right now. We're dealing with their structure as algebraic things. Okay, so we're trying to break them into pieces as well as combine them and simplify them. So today we're focusing on this undoing of a double distribution, right? And then we'll get into some special cases and some hints and pro tips on things I've seen students struggle with and don't need to moving forward. So if you just recall what I mean by double distribution, or we call it the double-double, right? Double-double distribution, which is when I had something like x plus 2 times x plus 5. And we said, multiply and simplify. So this is back in chapter 1. This is like 1.4-ish. And what we would do, we would distribute it just like we normally would with anything that's being multiplied to something within brackets. We distribute a x times x plus 2, and then distribute it also to the 5. All right, so whatever's in front of the brackets got distributed through. And then we did the same thing again with each of these, the x and the plus 5. It's a plus 5. Both got distributed through. And so we'd be left with what? X times x gets us x squared plus 2x. And then here we've got a plus 5x. And then 5 times 2 is a positive 10. Okay, I'm writing these middle terms in a different color because we need to kind of hold on to those. We would collapse this at the very end by saying, okay, this is all, x squared then plus 7x plus 10. So this is how we would multiply and then simplify an expression. Now we are looking to go in the opposite direction with this unit, right? Remember I was talking about the importance of breaking things into their components or where they came from can actually help you solve problems in many different ways. So how can we break this into what must it have come from, right? What was distributed to get me? So if I, covered up all of this, I didn't give you any of that, and I said, this came from a multiplication, right? What did it come from? You'd have to figure out how that process went and undo it. So I'm going to use this example and pretend that we didn't know any of this and go back through the process. But first I want to just highlight this 7x, okay? This came from the sum of these two terms. And if I changed these numbers around, we've done a lot of these. If I change these two numbers around, that's going to change these numbers here as well, which will change here and here, right? But essentially, it will always be the case that I have some middle terms like this that do reduce to the 7x. That's if these are both what we call linear pieces, where they each have degree 1, okay? We have a lot of problems that look like this and a lot of problems that look like this. This is a special form called a quadratic or a degree 2 expression. So what I'm just trying to get at is that these all look very similar. If I did another quick one here, just to drive home the point. If I had x plus 3 times x minus 4, and I did a double distribution, I'd get, what, x times x plus 3 minus 4 times x plus 3. And then I distribute again, I get x squared plus 3x for that first one, minus 4x, and then minus 12. And then these would collapse again, right? And I'd get negative 1x minus 12. And that's as simple as it gets. Again, I'm just showing you that these middle terms collapse to get you this third term. So it's like we should have had 4 terms after we distributed, but what we're given is 3, and we're asked to go backwards. So that's the challenge of these problems. Okay, I'm going to erase this because I want to keep with the one we had before. But this is essentially the issue. We have a 3-term expression that came from, most likely, a double-double. So if that was the case, how do we figure it out? So let's say now, let's pretend, given x squared plus 7x plus 10, factor as completely as possible. So there's 2 things you need to look for. And it's really the relationship between this term and this term. A lot of times this guy is going to be just x squared because we're multiplying these 2 x's times each other right here, right? So this term is pretty much determined by that multiplication. This term here and this term here are determined by x times 2 and the 5 times the x here. And then this last term, this plus 10, is determined by this 2 times this 5, right? Or this 2 times this 5. When all the distribution happens, that's where those terms end up, right? This 5 gets multiplied by this 2, and then that becomes this last term. And just like the last one with the 3 and the negative 4, it became, what, negative 12. If those were the numbers we used. Now my memory's gone. That's okay. So it's always the case that these last 2 terms end up as this last term, and the middle 2 terms end up as this combination of the inner pieces, right? Where the coefficient gets multiplied by the one variable. So to go backwards on that, we're looking for the values that add to this 7x and multiply to the positive 10. What terms add to 7x whose coefficients multiply to 10? Right? Well, to add up to 7x, I'm going to need something x plus something x, and this will need to equal 7x. And we need that these 2 coefficients equal 10, right? Because of the way that they distribute through. So we know, from before that 2x plus 5x does this, because 2 times 5 is 10 and 2 plus 5 is 7. So this is why this worked out and this worked out. Okay? But if we didn't know that, we'd have to do some trial and error. So what you do is look at 10 and think, all right, well, what multiplies to get 10? I could do, 1 and 10, 2 and 5, and that's it. So if we had instead chosen 1 and 10 to start with, so well, 1 times 10 equals 10, but does 1x plus 11x equal 7x? And no, you should see that that's equal to 12x. That doesn't work out. So we know that these won't work, and we went in and checked 2 and 5, and that did work. So what that tells us is that x squared plus 7x plus 10 must have come from x squared plus 5x plus 2x plus 10. Right? That's these middle terms that we were looking for. I actually want to include the sign in those. Because 5 times 2 is 10, and 5 plus 2 is 7. And so from there, then we can factor by grouping. right? And you get x times x plus 5 in that first group. And then in this second group, we'll get plus 2 times x plus 5. And then we can factor by grouping again. Oh, this must have been distributed in as x plus 5 to x plus 2, right? X plus 2. So that's how we go backwards. Okay, that's how we undo double distribution. You have to break apart this middle term into the two terms that can work. Usually it's, not usually, if it's possible, it's just going to be one pair that works like this. The order doesn't matter, usually, but there's only going to be one pair that works. It doesn't always work, okay? I'll show you an example of that as well, but first let's do one where it does work. So, find, let's just say factor as completely as possible. And we've got something like this. So let's say x squared minus 6x plus 8. So again, what we're going to need to do is find factors of 8 that add to negative 6x, right? Because we're looking for something where it's x squared plus, let's do it like this, x squared plus blank x plus blank x plus 8. So we've got to think of factors of 8. So do some side work up here. We think, well, we've always got 1 and 8. That's always an option. You've got 2 and 4. But since there's a negative sign here, we also need to include the possibilities of negative factors. So we should think of -1, -8, -2, -4. You say, why are they both negative, Mally? Why not one negative and the other? Because what's the sign of this 8? It's positive, right? So we need to think of factors that multiply to positive 8. So it's only going to be things that have the same sign, either +1 and +8 or -1 and -8 together. So what we want to do is try each of these out. So if I tried, 1x and 8x, is that going to allow me to get back to this -6x? No. So that's not going to work out. What if we tried 2x and 4x? Well, what does that combine to be? That combines to be 6x, but it's positive, right? So that doesn't play. It was close, but in the other direction. So you can use a little bit of logic here to say, well, then -1 and -8 aren't going to do it either, right? So if it's going to happen at all, it's got to be these two, -2x and -4x. It must have come from splitting it like this. Well, does that add up? Yeah, that becomes -6x. So this is the working pair. So then what we do is we again factor by grouping. So it's like our second step. Our first step is find possible pairs that have this quality of adding to the middle term and multiplying to the last term. So factor by grouping now. And we get x times x minus 2. And then we've got a plus -4x plus 8. So what we can actually do is pull out a -4. So if I pull out a -4, what that's going to do here, let's do some side work. So I've got -4x plus 8. If I pull out a -4, what must have been distributed? That will keep this x term a positive x. But -4 times what gives me positive 8? -2. And you might see the reason why I did that is because I want this to be the same factor as this, if possible. So that's why we pulled out that -4. Last step, factoring by grouping. I've got this x minus 2 as a common factor, so I get x minus 2 out front times x plus a -4 is just x minus 4. So that's factored. Okay, that's broken up in the way that we know works. How do we know it works? Because if we multiplied it out, it would look like what we do in this direction, right? It's exactly the same. We've just gone backwards. All right, so I'm going to do one more here. Before I give you some tips. Well, actually, this is one pro tip. And it's always try the GCF, not the CGF. I don't know what that stands for. The GCF, greatest common factoring, first. Okay? So if we had something like this, like 2x squared plus 6x plus 4. Let's see if that works. Yes, it should. So here, if we're breaking this up into, factors, it's no longer the case that my first term is the same, right? X times x doesn't get me 2x squared. One would have to be 2x, and one would have to be x. And that actually makes this a lot more complicated. It's not impossible. It's just more work. So what you can do is first look for a GCF. So do we see a GCF here between these three terms? Yeah, they're all even at least. So we can take out a factor of 2 from each of them. We'll be left with x squared plus 3x plus 2 on the inside, right? Factoring out a multiple of 2, or a factor of 2, rather. So now we're left with x squared plus 3x plus 2 on the inside. Again, I did that to reduce this term's coefficient to 1 on the inside, so that now this looks like the problems we've done above. But this one's now a little bit easier too, right? So what factors multiply to 2 but add up to 3? So we'll write this down here. 2 times what? X squared plus what x plus what x plus 2. So what adds to 3 and multiplies to 2? Well, that would be just 1 and 2. Right? 1 times 2 are the only factors of 2. It's prime. So we've got what we need. So now we can do factoring by grouping. We're just inside this bracket. So here we've got equals 2 times, got x times x plus 1. Plus, and then we can factor out a 2 from this set, 2 times x plus 1. And then we proceed as we normally do, factoring by grouping. We take out this binomial to be x plus 1. But again, this is inside these bigger brackets, so don't lose that, times what was left over. We had x plus 2. So now this is completely factored, and you can actually drop these outer brackets. Why is that? It's because multiplication is associative, meaning it doesn't matter once it's all multiplication like this. Got 2 times this, that I can rewrite it as just 2 times x plus 1 times x plus 2. And again, why associative property? Worth reviewing. Allows us to drop these brackets and just write it a little bit simpler. Not a huge deal. So this is the pro tip. To make them easier, and if this first term isn't 1, which, is what we kind of rely on to do these in an easier way, then you need to factor out a GCF. Now, the other thing I want to show you is that sometimes it's not possible. Right? If, 2, 5, 7, 11, 13, all these things are prime. So, second degree expressions can be prime too. So meaning, we'll say, notice this. X squared, let's see, how do I want to do this? Minus 4x plus 4. So if I wanted to factor this, this is pretty easy to do. We see that this is really x squared minus 2x plus 4. Right? We see the negative 2 times negative 2 equals a positive 4. And so this ends up being factorable, and we get x minus 2 times x minus 2. So it's not so bad. However, if we look at something that looks really similar, x squared minus 4x minus 4, I might say, oh, well, it's like basically the same thing, right? I should be able to factor this. And you go looking for those middle terms, plus blank x, that multiply to negative 4 but add to negative 4. Well, now you start thinking about, okay, well, what's the factors of negative 4? Well, I can have negative 2 and 2. I could have 2 and negative 2. I could have negative 1 and 4. I could have negative 4 and 1. Right? Obviously, these are the same, but we could switch the order around. So we try each of those. Negative 2 and 2. Right? Well, negative 2 plus 2 gives me 0, so that's not going to work out. So both of these are gone. How about negative 1 and 4? Well, negative 1 and positive 4 gives me, what, positive 3? Well, that's not negative 4, so those don't work. And then how about the last set then? Hopefully this works out. Negative 4 and 1. Negative 4 and 1 gives me negative 3x. That's not going to do it either, right? So what the heck? This thing is prime. And so just kind of notice how this looks very similar to something that is not prime. And it's not because this is positive, this is negative. Don't draw any connections there. What I'm just saying is that sometimes it doesn't work out. And so you have to go through all of these factors to explore all possibilities. You will get faster at this, just like the other things. But you need to exhaust all of them before you say that it's prime. Okay. So same thing applies before as well. Always try the GCF first, and then always exhaust all possibilities to see if it's possible or not. I'll say here, a lot of students give up prematurely on this. And what I mean by this is that maybe you don't think through all the factors, or something like that, or we don't see a certain combination, we didn't switch the signs, and we just say, oh well, this one must be prime. They're pretty rare, and on an assessment situation, a lot of times we're going to want to see that you can factor, as well as notice if something's prime, but just to see it through to the end. I'm not saying keep trying for hours and hours, but don't give up immediately. There might be factors you're not thinking of, especially if they're numbers you're not super familiar with, right? Like, what are the factors of 39, 3, and 13? Not many people, kind of remember that 39 has factors right out the gate. So that's the last note there. The other thing that I wanted to talk to you about was special forms or special cases. And this is one of those places where people might see or say, seems weird, so maybe it's just prime. So if I have something like this, x squared minus 25, and I wanted to say factor this thing. So there's no middle term here. That is not a problem. Again, because there kind of is a middle term. I could rewrite it like this, right? Plus 0x is a middle term. And you say, okay, Mally, haha, I didn't know we were playing opposite day, right? Or this was a trick question. It's not a trick question. You can always write in something being added 0 to it, because it's always the same, right? It's like, say, I have $20 in my pocket. I also have 20 plus $0 in my pocket. That's true. And the reason that we do this is so that we can be creative about that 0. What does 0 really mean? 0 really means, right, like negative a plus a is always 0. This is this truth about the real numbers, right? Algebraic truth. And we can use this to our advantage when this number is special, right? In other words, when this number, when its factors add up to 0. And so that is the case when this is a perfect square, right? When it's a perfect square, what do you know to be true about it? That, 2 squared is 4. What is 2 squared? It's 2 times 2. 3 squared is 9. That's 3 times 3, etc. 5 squared is 25, which is 5 times 5. And so what we can do is say, well, wouldn't this be the same as x squared plus 5x minus 5x minus 25? Would you agree that this 0x term came from plus x or plus 5x and minus 5x? Hopefully you'd see that and agree. And so from there, can I do factoring by grouping? So yeah, I can pull out an x from this first group, right? X times x plus 5. And then in the second group, I can pull out a minus 5. Right? And if I pull out a negative 5 from both of these, I'll get negative 5 times x plus 5. It'll switch the sign here. And then I can pull out that x minus 5, and I'll be left with x, did I say minus? I meant x plus 5. So we pull out that x plus 5, and we're left with what on the inside? X minus 5. And so we get this x plus 5, x minus 5 is actually the factored form of this. Right? It didn't have a middle term, so it didn't really look like it would come from a double-double, but it did. And it's because of this fact here that we took this 0x and split it into a plus and minus of the factors of the third term. Okay? With the coefficients as factors of the third term. So this only works with things that are exactly of this form, and that form is x squared minus a perfect square, so like x squared minus 9. We can rewrite this as, well, hey, we don't have a middle term, so really this could be written as, and let me do it like this, like minus 3x plus 3x minus 9. And then again we can factor by grouping, so that first group is x times x minus 3. That second group is 3 times x minus 3. And then we pull out an x minus 3, and we're left with x plus 3 on the inside. And so this is what this came from. So this is what we call the difference of perfect squares. And it comes from exactly what the structure of this thing is. We've got two perfect squares here and here, and they have a difference between them. Okay? So they will always factor in this way as long as you have perfect squares as your first and second term because it means that middle term must have been 0. We can split the difference, haha, and then go through and wrap up the factoring. So here's a pro tip, common pitfall. If we were to be asked factor x squared plus 25 as completely as possible, these are the 2 wrong answers I see the most. Okay, so one I'll see is, oh, well, we just take, this isn't liking me today. It's x squared plus 5 squared, so it's x plus 5 squared, right? Why is that not right? Well, what's x plus 5 squared? X plus 5 squared is a double-double, and if you do this out, it should be x squared plus 10x plus 25, right? It's going to have that middle term. This doesn't have that middle term, so that's not right, and it's shortcut thinking. Our brains try to trick us into, well, this is simpler than it looks. We should just do blank. Really think it through, rely on what you know. Don't try to skip steps. The other one I see is that we just see, oh, 2 perfect squares, bada bing, bada boom. It must be this, right? Because we got the x's and we got the 5's. Why does this not work? Well, I know that if I multiply this out, I actually should end up with x squared minus 25. Is that the same? No. So this is not the difference of perfect squares. This is the sum of perfect squares, which is not factorable. There's nothing that you can do to get this to work, because if I break this out as x squared plus, apart from these wrong answers now I'm just trying to look at it. So if I put in that imaginary middle term, what are the factors of 25 that could add up to 0, of positive 25? I've got 1 and 25, I've got 5 and 5, I've got negative 1, negative 25, and negative 5, negative 5. Neither of these are going to add up to 0. Right? I'll get negative 10, I'll get 10, I'll get 26 or negative 26. So it just doesn't work out. So it turns out that x squared plus 25 is prime. Or you could say not factorable. Okay, but now you've encountered pretty much all the different types of factoring problems you'd see in this course. They can get more complicated as you go on, but they're really just variations on the themes we've covered here. So this is a special case when you don't see a middle term. If it is a difference of perfect squares, you can factor it like this. Always try the GCF first, right? Sometimes these trinomials or 3-term expressions are prime. But trying the GCF first and trying to look for that middle term, how to break it up so that it works like this every time, is the key. Other shortcutty ways of doing this are, again, really problematic, so just to rely on what makes sense. And what makes sense is that this comes from distribution the way that we've always done it and the way that it has always worked, right? 100% of the time. So with that, you've just learned how to undo double distribution. You learned about the special cases and some of my pro tips for students. I hope you have fun with these, kind of playing with them as like puzzles. But again, remembering that these are tied to things from the real world that are degree 2 expressions or functions, which are the kind of lead-in point for college algebra, where you're most likely heading next. Alrighty? So have fun, and we'll see you in there.